In this AC circuits lab, we're going to use this series LRC circuit to study the resonance of this type of circuit and also to make predictions and test them about what will happen when we put various types of components in series and parallel. The lab manual for this lab is at lightandmatter.com. The lab is called AC Circuits. It's in the Physics 222 lab manual. And I'm going to assume that you have that in front of you while you're watching this video, so I don't need to explain everything quite as much. Also, since the RC Circuits lab that comes before this involved lots of learning how to use the scope and triggering, I'm not going to explain very much of that for this lab. So here's our circuit. We've got the same function generator we used for the RC Circuits lab. Then we go to a 470 ohm resistor, a capacitor, which is 0.022 microfarads, and then this coil whose inductance we previously estimated as a homework problem to be about 1 Henry. Before we go on, as described in the lab manual, I'd like you to pause the video and take a minute and copy this table down into your lab manual and summarize what you know about how resistances, capacitances, and inductances combine in parallel and series. So please pause the video, take a second, and do that. Okay, I've got the oscilloscope powered up now. I'm going to hit the default setup button, which is always a good idea. And now when I want to use the scope to measure a voltage difference from this circuit, I'm constrained by the fact that this input to the scope on the black side and this black output of the function generator are both grounded. So that means I have no choice but to connect that side of the scope's input to that. Otherwise, I would effectively be shorting across something I didn't want to short across. Then, because I've arranged the circuit with the resistor connected closest to that black plug on the function generator's output, what's naturally going to happen is I'm going to end up plugging in the other connector to the input of the scope on the other side of that resistor, so I'm measuring the voltage across the resistor. I could measure other voltages in the circuit, but I would have to rearrange the circuit. So for instance, if I wanted to measure the voltage across the inductor, I would have to move the inductor physically over to this side of the circuit so that I can measure its voltage while still being grounded. This is a series LRC circuit, and so it has some impedance, which is the sum of the complex impedances of the resistor, the capacitor, which is off screen, and the inductor. And so a nice way to think about this measurement is that although we're measuring a voltage on the oscilloscope, that voltage across the resistor is proportional to the current in the resistor by Ohm's law, and that means we're effectively measuring the current in the circuit. And so we're applying some voltage to the circuit, which is an AC voltage coming from the function generator, or we will when I turn it on. And we're measuring the amplitude of the current that flows as a result, so we're getting the response of the circuit, which is a measure of its impedance. I'm going to go ahead and turn on the function generator now. When it comes on, its amplitude is set to 0 volts, which is probably a good thing for safety. You do need to be careful if you're in the real world working with this kind of thing. When you have an inductive load like this, it stores a lot of energy in the magnetic field, and it can be quite dangerous in terms of electric shocks. And in a resonant circuit like this, when I'm close to resonance, the voltage across some of these components, like the inductor, can be a lot bigger than the voltage put out by the function generator. So right now it's on 0. And now I'm going to go ahead and turn up the voltage to, so it comes on at 1 volt, which is a lot more than I want actually for safety. So I'm going to move the cursor, and I'm going to turn that down to 1/10 of a volt for safety. I realize it's a little hard to see some of the smaller fonts on some of these readouts. I've moved the camera in fiddled around with the brightness and the focus a little bit. Although I was referring to these amplitude numbers down here on the function generator, we actually don't need those anyway. So it probably doesn't matter that much that you probably can't see them on the video. For parts A through D of the lab, we're going to be measuring the resonant frequency of this circuit as we change various things. So that means all we need is a relative measure of the response of the circuit, and then we maximize that response by fiddling with the frequency and see when we get the strongest response. That would be the resonant frequency. So that means that the numerical data you actually need to get from the video is this number, which is the frequency from the function generator in hertz, and that I think is big enough that you can see it pretty well on the video. So I'm now going to use the volts per division knob on the scope to make that sine wave bigger so I can see it. The triggering is obviously terribly messy in a way that kind of doesn't matter for my current application right now, because all I'm trying to judge is the response, which is basically how tall is that sine wave. So I'm not even going to worry about messing with the triggering right now. So I'm going to play with the frequency and see what happens. First I'll try lowering the frequency. I'm at 1,000 hertz, which is actually pretty close to the resonant frequency you'd expect. And in fact, you should stop and do what the lab manual says to do. Pause the video and estimate the resonant frequency of this circuit before we actually verify it experimentally. So once again, the values of the components are 470 ohms for the resistor, 0.022 microfarads for the capacitor, and we've estimated about 1 Henry for the inductor. So pause the video, predict the resonant frequency, and remember that if you calculate an omega, you're going to want to convert that into an F frequency, because that's how this function generator reads. So pause, calculate that, and then we'll start again. Okay, so if you've done that estimate, you have some idea of what frequency we expected. However, because the estimate of the inductance of the coil was really rough, we don't actually expect to be that close to the true resonant frequency. So we're just going to go ahead and empirically find out what frequency optimizes the response of the circuit. So if I play with the frequency knob, right now it's changing the ones place, which is not enough of a change. So I'm going to move the cursor over so that when I turn the knob, it's changing the tens place digit. And I'm going to try turning down the frequency and see what happens to the response. So I think you can see that the response is getting smaller. So we're going the wrong direction. So I'm going to go the opposite way. And we expect two things to happen. One is we expect that this will change because we're changing the frequency, and the circuit responds at the frequency it's being driven at. We also are seeing, though, that this is changing. So if my purpose had been to show this change, I would want to clean up the triggering, but I just don't really care about that right now. So higher frequencies are still giving me bigger responses. I'm going to keep on going to higher frequencies. Still growing. The triggering is cleaner now because we have a better signal-to-noise ratio. I need to change the scale on the y-axis now that I'm getting such a big response. And there, as I continued going up in frequency, I passed through resonance. So the response maxed out and then came back down. So now I'm going to go back down in frequency. I'm now at 1250 hertz, which is above the resonant frequency. And it looks like that's pretty close to resonance. I'm going to move the mouse cursor over so that I can play with the ones place in that hertz value. I'm going to crank up the scale. Oh, I can't. Oh, there we go. And I'm going to see if I can tweak that just a little bit more and find exactly the right resonance frequency. That's getting worse. Better. So I think somewhere around there is about optimal. So I'm going to call it 1190 hertz. So at this point, you should compare what you got for your estimate and verify that it's reasonably close to this. It shouldn't be off by more than about 10 or 20%. If you were off by more than that, go back and figure out what went wrong with your calculation. Now we're going to do part B of the lab, which involves changing the capacitance in the circuit and seeing what effect that has on the frequency. So as it's described in the lab manual, you're supposed to go ahead and predict that and then do it and see if your prediction is right. We're going to change from that capacitance to this value. This value is the one that we measured in the previous lab. We measured it by several different techniques, and I think that's probably a rough estimate to within about 10% of what it actually is. The resonant frequency was this, and now when we change the capacitance, that frequency is going to change. When you make your prediction of the new resonant frequency, I want you to use ratios to do that. So figure out the proportionality. The frequency is proportional to C, to some power, throwing out all the other constant factors, which aren't going to matter here because we're not changing them. That cleans up the calculation a lot and makes it simpler to understand what's going on. Please do not do anything silly like extracting the value of the inductance and then plugging everything back in numerically with units. That makes it more complicated and harder for you to understand what you're doing. So you should be practicing your skills with reasoning about ratios and proportionalities. So please pause the video now and fill in what number you expected in that box, and then we'll do it. I flopped the circuit around a little bit so that you can see the capacitor we're going to take out. And then because I don't want to get a shock, I'm going to go ahead and turn the voltage on the function generator down before I touch any of the conducting surfaces. Even though it was only 1/10 of a volt from the function generator, it could still be a lot more since we were right near resonance if I'm talking about the voltage on one of the actual components. So taking out that capacitor, putting in this one, which is exactly the same capacitor we used in the RC circuits lab. Okay, so if you went ahead and did that calculation now, I think your prediction should have been a smaller frequency because we're making the capacitance bigger. And I still got the function generator on the same resonant frequency it was at before. I've got the amplitude turned down to 0, so I'm going to go ahead and turn up that amplitude to 1/10 of a volt. We're getting quite a strong response, quite a weak response now, since we're way off resonance for the new setup. And so since I'm expecting the frequency to go down, I'm going to go ahead and turn that frequency down and see what happens. So sure enough, as I turn the frequency down, I'm getting a bigger response. And then I went past the peak, so I'm going to go back up in frequency and try to tweak it for a maximum. Small adjustments now to see if I can get it just tuned in. So that's about it. I'm getting 844 Hertz for my resonant frequency. This is part C of the lab that we're going to do now. So I've switched my capacitance back to its original value, the little blue capacitor we had before. And now I'm going to take this huge coil and I'm going to replace it with 2 such coils in series and also 2 such coils in parallel. So if you remember at the beginning of the lab, I had you make up that table of how resistances, capacitances, and inductances combine in series and parallel. Use that and figure out what should happen to the inductance of this coil when I put 2 of them in series or 2 of them in parallel. And then use that to predict what should happen to the resonant frequency of the circuit. So please pause the video for a second and do that. Okay, so at this point you should have your two predictions written down. The first one would be for this setup, which I now have. I have the two coils in series, and so you should have your calculation figured out of what the resonant frequency should be with those, and also your prediction for what I'll do after this, which will be the two coils in parallel. Okay, so I'm going to turn on the function generator, which I had turned off while I fiddled with the circuit. It comes back up on its default frequency of 1000 hertz. I'm going to turn up the voltage to 1/10 of a volt again. And now for the series setup, I've predicted that the resonant frequency should go down relative to the original setup. You should have a number predicted for that. But if the original setup had a resonant frequency of about 1190 hertz, I'm expecting to have to go down from there. So let's first go to 1190-ish. So now we're around that frequency and we're not getting very much response. So now I'm expecting that I should have to go lower now to get the resonance on this circuit. Let's see if that's true. Going down in frequency, the response is getting stronger. And then I went through the resonance, so I'm going to back up a little bit, try to tune it in as well as possible. Fine adjustments. I think that's about as close as I'm getting. So that's 847 hertz with the two inductors in series. So for the series case, I got excellent agreement with my prediction. One thing to realize here is that that prediction should probably be pretty good, except maybe for the fact that these two coils each have magnetic fields, and those magnetic fields superimpose, and so it's not necessarily a perfect approximation to say that these things act as separate inductors. So this is called the lumped circuit approximation. So the fact that I got great agreement with my prediction means that the lumped circuit approximation apparently is pretty good. I've now switched to the parallel setup. You can tell it's parallel, no longer a pure series circuit, because there are junctions in the circuit now. So back here at the function generator, you can see that there were two blue wires plugged in there, one there and one there. Those are going off to the two coils. And then we come back on the other sides of the coils with these yellow wires. Those yellow wires come together at a junction here. So now those two coils are in parallel. So now I'm going to turn on the function generator. It goes back to its default frequency of 1000 hertz. My prediction was that the resonant frequency would now be higher, so I'm going to start going up in frequency. And before I do that, I have to turn up the voltage. Okay, so now I have a signal coming in, and now I'm going to start going higher in frequency. I am seeing the response get bigger, which is what I predicted. It's a little bit off scale here. And actually, it was just going off scale as I went through resonance. So maybe I can get away with having it at the more sensitive scale so I can see better. And now I'm tuning in that resonance. Somewhere around there, I think, so 1671 hertz. Okay, we're ready to do part D of the lab now. So I'm back to the original circuit with a single inductor over here and the original blue 0.022 microfarad capacitor here. I've got a second capacitor exactly like that one, and I'm going to put those two capacitors in series. So again, I want you to make a prediction. So look back at that table you made at the beginning of the lab. Look at how you expect capacitance values in series to combine. Predict using ratios how you expect the frequency to change. And once you've had your new frequency predicted, you can restart the video and we'll test that. So please pause the video and do that prediction. Okay, so I'm going to now put these two capacitors in series. Red wire is going to be the one connecting one capacitor to the next capacitor. I'm going to go to that capacitor. And finally on to the rest of the circuit. So now I have those two capacitors in series. If that's not really visually obvious that they're in series, just note that there are no junctions anywhere in that circuit. Turning on the function generator again, and I predicted that the resonant frequency was going to go up by putting the two capacitors in series, and you should have actually predicted a number for that. So I'm going to go ahead and turn this on. And now I'm going to start going up in frequency. The response is getting stronger. Close to the resonance now. I think that's about it. So 1644 hertz. Now we're going to do part E of the lab. It's pretty hard to show all of the details with this on the video camera, so you're definitely going to want to look at the circuit diagram. But the basic idea is that to avoid problems with grounding, we're now going to drive the circuit inductively. So right now, the function generator is going straight to this coil. There's nothing else in that circuit. And then we're going to have an air gap here between that coil and the rest of the circuit, which we're going to drive basically like a transformer. Now I put in a second coil. This coil on the right is going to be the one that's going to be part of my LRC circuit. Now I've got a series LRC circuit which connects the inductor through the resistor, through the capacitor, and back to the inductor. So normally we wouldn't expect the circuit to do anything because it has no voltage source or source of energy, but it's going to be driven by the other inductor over there. Now I've got channel 1 of the scope hooked up so that it measures the voltage across the inductor. And now channel 2 with the black wire and the blue wire is hooked up across the resistor. To make the connection with the black wire, actually I simply connected the ground side of channel 2's input to the ground side of channel 1's input. Those are both grounded anyway, and they're both supposed to be connected to the same point in the circuit. Now on the scope, I've only turned on channel 1 so far, and I'm just going to power up the function generator, which is driving the first inductor, and verify that I actually get a response in my circuit, which now has no physical connection to that inductor. There's just an air gap in between. So if I turn up the voltage, I get a massive response in the circuit. So essentially I'm sending a radio signal between one side and the other. turn that down a lot. So channel 1, if you look in the lab manual, that's reading the EMF across the second inductor. So what's happening there is that the changing magnetic field from the first coil is producing a curly electric field in the second coil, and that's exactly what we're reading on the scope right there. So this is directly analogous to the earlier lab we did with Lenz's law. I'm going to verify that I can see the resonance again by turning the frequency up to what we previously saw. So now we're right around the resonance from before. And now, because we're interested in seeing the actual phases of the signal for this part of the lab and the amplitudes, I am going to fiddle a little bit with the triggering and try to get it looking better. So if I go to the trigger menu and change the mode from auto to normal, you probably can't read that text right now. Now I can play with the triggering controls manually, and even though it says slope rising right here, I've got so much noise on my signal that it's actually triggering half the time on a rising slope and half the time on a falling slope. So to improve the signal to noise ratio, I'm just going to make the driving force stronger. So I'm going to turn up the amplitude on the function generator to a volt. At this point, I probably really don't want to touch the conducting surfaces on my circuit because I would probably get a nasty shock. I'm going to turn the scale back down. So that cleans up that signal a huge amount, and because it's cleaner, the triggering is cleaner. So now I'm ready to start using channel 2 of the scope, which is reading the voltage across the resistor. And as before, that voltage across the resistor is essentially a measure of the current in this series circuit. So to turn on channel 2, I hold down the channel 2 menu button, and that signal pops up. And it's got its own scale. So over here, the font is impossible to read in the video, but channel 1 right now is set at 5 volts per division, channel 2 is set at 1 volt per division. I can also move these up and down. Often it happens when you're using a scope with both channels, you're not sure which trace is which. So here's the vertical position for channel 1. So that verifies that that trace, as we knew before, was channel 1. And now I can use the vertical position for channel 2 and get that down there if I want. If I now go back to the trigger menu by pushing the trigger menu button right here, it's telling me right there that the source for triggering is channel 1. That's clearly a good decision because if you look at those two graphs, you can see that the signal to noise ratio is much better on channel 1 than that fuzzy channel 2. So now we want to observe the phase relationship between these two channels. And the first thing to realize is that because of the way we had to hook up the circuit because of grounds, really one of these traces is inverted compared to the other, just for artificial reasons. If you look at the circuit diagram, the inductor has the red on the left, the resistor has the red on the right, and you can also see that physically in the way these are laid out on the inputs of the scope. So that means that if we really wanted to compare the phases of these two signals, we really have one of them flipped compared to the other for reasons that we don't want. Turns out the scope does have a way to flip one of those signals if we want to. I'm going to go ahead and flip channel 1. And so to do that, I'm going to press channel 1 menu And then down here near the bottom it says invert off. I'm going to push that button and it's going to say invert on, and watch what happens to the traces on the scope. So it flipped that trace. So now this is more of a true measure of the phase relationship of those two channels. So if you look at the circuit diagram in the lab manual, positive now means that the right-hand side of the inductor is at a higher voltage than the left-hand side. And positive also means that the right-hand side of the resistor is at a higher voltage than the left-hand side. I think you can already tell that these two traces are not in phase with each other, but to make that easier to see, adjust the seconds per division knob. That might make it a little bit more obvious. Maybe that's too much of a zoom right there. And so the peak on channel 2 is occurring after the peak on channel 1. And recall that the peak on channel 2 is effectively a measure of the current through the inductor. The peak on channel 1 is directly measuring the voltage across the inductor. So that tells us the direction of the phase shift. And then to measure that phase shift quantitatively, I think you can see that that peak is lining up almost exactly with the maximum slope on that one. So it's almost exactly a 90-degree phase difference. If I zoom in one more level, you can't really see the whole cycle anymore, but I think it's pretty visually convincing that that peak is almost exactly 90 degrees after them. It's a little bit more than 90. It looks like it might be, 95 or 100 degrees, but very close to 90. So now, as it says in the lab manual, you should stop and try to explain this phase relationship based on the physics you know. So now we're ready to do part F, and before we do part F, I want you to go ahead and make the prediction that the lab manual asks you to make. So you're supposed to predict the complex impedance of the capacitor, including both its magnitude and its argument. So pause the video right now, work out that prediction, and we're doing that prediction at the frequency we're at, which is the resonant frequency of 1192 Hertz. Okay, so as described in the lab manual, you do need to rearrange some things for part F. So the lab manual leaves it up to you how to do that, but since this is not a real lab, I had to make that decision. So this is what I came up with right here. So the circuit elements in the circuit are just kind of reshuffled a little bit. Channel 1 is across the capacitor, channel 2 is across the resistor, so it's effectively measuring the current through the capacitor. And I left the scopes set up the same, so channel 1 is still inverted just as before, and that makes the signs of this reading and this reading consistent with each other. So the scope is frozen because the function generator is off, so there's no signal, it's not triggering. So I'm going to turn on the function generator and turn up the voltage. And I think you can see there are some little spikes on that bottom signal. That's probably some kind of internal interference in the scope that we saw earlier in the RC circuits lab. It'll probably go away if I change the time scale though. And now I want to go ahead and measure both the amplitude and the phase of these two signals. The amplitude is going to be an absolute measurement. The phase is going to be a relative measurement. So for the amplitude, let's first measure channel 1. So I'll press the channel 2 menu button. to make that go away, I guess you have to press it twice. So we're going to measure the amplitude of channel 1. Scoot it into a convenient position. Crank it up to the maximum magnification that still lets me see the whole signal. I'm going to line up the bottom of that trace with one of those dashed lines. And then for the top of the trace, I'm going to scoot it over horizontally so that it's against the tick marks on that y-axis. Should make it easier to get a reading. And so what I'm getting is a peak-to-peak amplitude of 1, 2, 3, 4 point something. And it looks like I'm going to call it 4.35 divisions. Now I've switched to channel 2, and the amplitude is now, as close as I can tell, 1, 2 and a half. So 2.5 divisions. And the scale on this axis, which you can't really see there, is 100 millivolts per division. And by the way, I said earlier that we were going to measure all of this stuff at the resonant frequency, but actually in between now and then, I turned the function generator off and on, and so now we're actually at 1,000 hertz, which is slightly off resonance. So in your analysis, you really want to use 1,000 hertz, not the exact resonance frequency. Okay, so there's a recap of the data we got for the magnitudes of those, the amplitudes of those sine waves. 4.35 divisions and 2.5 divisions with those scales. And so by using channel 2's data, you can take the known resistance of the resistor and figure out the amplitude of the current. So then you know the amplitude of the current in the circuit and the amplitude of the voltage across the capacitor. So that gives you an experimental way of determining the magnitude of the impedance. Now we want to find the argument of the impedance, which tells us about the phase between the current and the voltage on the capacitor. Okay, so to determine that phase, the phase is a relative thing, not an absolute thing, so I need to have both channels on. So I'm going to bring channel 1 back, scoot it up a little bit. Channel 2 is looking so ugly, I'm going to turn its scale down. And now I want to zoom in on the time axis. So I think you can see that the peak of channel 2 is coming earlier than the peak of channel 1. And if that is the steepest part of channel 1, then that does pretty much coincide with the peak of channel 2. So channel 2 is about 90 degrees in phase ahead of channel 1. So there's a summary of all of our data for part F. With all of that put together, you should be able to get a purely empirical determination of the complex impedance of the capacitor at this frequency. And by the way, I turned off the function generator and turned it back on again, so it's been on its default frequency of 1,000 hertz during part F. It hasn't been at the exact resonant frequency of the circuit like it was for some of our earlier parts.